Okay, so the next thing I want to discuss is the Lorentz group in 2 dimensions. Okay, so what is a Lorentz group? Let me first define it in general. The group of symmetries that connect. Well, let me be first loose, okay, loosey-goosey. Then we'll make it more precise, because what I'm going to say is correct in spirit, but not technically. Okay, so the group of symmetries of special relativity where I'm just trying to be very, let's just do it like this. And consider special relativity. We know that 2 inertial frames give rise to the same physics, right? The group of transformations that connect different inertial frames in special relativity are known as the Lorentz group, okay? So if you have done any special relativity, suppose that, so we are doing a 2-dimensional version of special relativity here. Suppose that you have some space-time, and the coordinates are described by some spatial coordinate x, and the time coordinate is t. And there could be another reference frame, which is moving with respect to, say, to this reference frame with velocity, say velocity beta. Beta is v over c, but we are going to take c, the speed of light, to be 1. Then this new reference frame has, say, coordinates x prime and t prime. Then x prime and t prime is related to the original coordinates x and t by a linear transformation, which is of the form gamma times t minus, say, beta x, and then gamma times x minus beta t, okay? So, and this you can write as, say, t prime x prime times a matrix gamma minus gamma beta minus gamma beta, and gamma acting on t and x. Beta, as I said before, is the speed of the reference frame divided by c, but we are going to measure speed with respect to the speed of light, so we can set c to be 1. Then And gamma, on the other hand, is given by 1 minus 1 over 1 minus beta squared square root. Okay. So these matrices form the Lorentz group. Okay, so this is the traditional way of looking at Lorentz group. Now I'm going to define the Lorentz group in a slightly different way, okay? Do you have any questions? This should be reviewed for those who have done some special relativity. If you haven't done special relativity, that's fine. Don't worry about it.
Sir, what special relativity?
Special relativity, Einstein's theory of special relativity.
Oh, sorry, you mentioned like a word before special relativity. Never mind, I probably missed it.
Some.
Oh, it's a sum. Okay, sorry.
Yeah.
Sorry.
At least these two equations should be familiar, right? Okay, so let me define the Lorentz group. So in special relativity, now one considers a space-time. For our case, we shall consider a toy space-time, a two-dimensional space-time, okay? Okay, so now let's draw a picture of the space-time. So this is the time axis, and this is the space axis. Okay, and one thing we will do is that we will set c, the speed of light, to be 1. That means that we will measure all speed relative to the speed of light. Okay. Now, take 2 points in the space-time. Suppose this is the point number 1, this is point number 2. These are called events. Why are they called events? Because they are both points in space and time. Okay, these are events. So suppose event number 1 is x1 mu. By x1 mu, I mean that t1 x1. So the mu is telling me whether it's x0 or x, the 0th component or the first component. The time component is labeled as the 0. And the second point, we are going to call x2 of mu, and that will be 2, t2, and x2. Okay, is this clear what the notation is here? The notation is very important.
Yes, sir.
Sir, could you go over the mu part again?
Yeah, so events are essentially x mu, and this is a 2 vector. It has x0 and x1. In our case, x0 is the time, and x1 is just the coordinate x, okay? And when I say x mu 1, this is a label for the point. Okay, so for example, this is 1 point, point number 1. So this label is meaning it's referring to point number 1. This is point number 2. This label is referring to the point number 2. Whereas the super index is referring to whether we are looking at the time coordinate or the space coordinate. the time coordinate or space coordinate, okay? Is this clear?
Yes, sir. Yes, sir. So the mu can be either 0 or 1.
Exactly.
Okay.
So now let's consider an interval between these 2 points. What is an interval? It's a length of sorts between these 2 points. So the interval, or more precisely, the interval squared between 2 points is given by delta S 1, 2 squared, and it's minus C squared T1 minus T2 squared plus X1 minus X2 squared. Okay. So this is an interval. This is what we define as an interval. Note that there's a minus sign in front of the time part. There's a plus sign in front of the space part. And in our units where C equals to 1, I can write the interval as del S1, 2 squared is equal to minus T1 minus T2 squared plus X1 minus X2 squared.
Sir, why do we have the minus sign here?
That's how I'm defining it.
Oh, I see.
Okay.
But why? Is there any?
Yeah, because
Is it the Lorentz metric? Like that's how
yeah,
the
it's a different
metric-
measure. It's not the Euclidean measure. It's a Lorentz measure.
Okay.
You will see that this is related to the fact that the Lorentz transformation comes out naturally. Yes, it's called the Minkowski metric. Okay, so I have defined a weird measure between any 2 points on my space. A space with such a notion of distance is called a Minkowski space. Okay, so Minkowski was one of Einstein's teachers who died very young, and Einstein actually named this space Minkowski space. So Einstein had a teacher who was inspired to write papers, based on his students' work. Okay. Maybe one day you will be famous and I will be remembered as your teacher. All right, so now let's define 3 kinds of intervals, okay? So this interval gives rise to, to 3 kinds of intervals, or they're more known separations. So for example, if I now redraw the space-time diagram, sorry about that. So if I redraw the space-time diagram, then can someone tell me if there's a like a beam of light or a pulse of light that emanates from t equals to 0 at the origin, what would be its trajectory? And
45 degrees.
45 degrees.
yeah, and that's because I have chosen the speed of light to be 1, right? And then we can also, extend it backwards. So this is known as a light cone. Okay, so now let's take a point at the origin. And now let's call then, then we say that this point is, say, x1 of mu is then 0, 0, right? And now we have a choice of x2 of mu. And let me just call x2 of mu just x of mu, because we have chosen one to be 0. And if I take the second point to be inside the light cone, say over here, then the interval is, what is the interval? Is it positive, negative, or 0?
Sir, it should
Positive, I
be negative because the t is larger than the x, the t interval
Oh, yeah,
portion.
t is going up, right?
Right. So this is a convention dependent. According to my convention, it's negative. Okay. So such two points which satisfy this are called time-like separated. Now, here, this point is in the future of this point, right? But if this point was over here, this would also be a time-like separation, right? But in that case, so let's call, in that case, this point would be in the past of this point, right? So for time-like separated points, they could be, this vector, you could imagine a vector in this direction. That vector is a future pointing vector. And a vector which would be pointing in this direction would be a past pointing vector, right? Is it clear?
Yes, sir.
Okay. Okay, all right, so this is the time-like separated, but what if, let me draw the space-time diagram again. By the way, space-time diagram is the modern way of doing special relativity. No more train platforms, no stuff like that. Okay, now suppose that, so I have again my event at the origin. Another event is on the light cone. In that case, what is delta S squared?
0.
Right. In that case, it's 0, right? Even though, delta T1 minus T2 is not equals to 0, x1 minus x2 is not equals to 0, but because of this minus sign, these two factors cancel each other out on the light cone. Okay, so 2 points which are separated like this are called light-like separated or null separated.
Is it like the two events are happening at the same time?
They're not happening at the same time, but if you could travel at the speed of light, then time would not elapse for you. They're not happening at the same time. As you can see, this is at time 0, and this is at a different time, but their separation is null.
So is the physical interpretation of the time light-like separation be that Like they're just separated by a light ray or a pulse.
Yeah, exactly. That you can reach this event from this event by a laser gun. Okay. So the last one is called, suppose that you have these 2 points, then what would be delta S squared?
Negative.
Negative.
Positive.
Positive, right?
I'm mixing up my conventions all the time.
Yeah, I know. I mean, I use the weird convention, the string theory convention and the GR convention. And some people use the particle physics convention. Okay, so such separations are called space-like separations. Now, can someone tell me, which one of these events happened before, this one or this one?
The center.
The what?
The central event. I mean, the event that's pointed
Okay.
in the center.
Is that an absolute fact?
Yeah, before and after I think is an absolute fact. Yeah. Or oh no,
In
no,
relativity,
no, it's not.
I mean,
it's
it
not,
depends
it's not.
on the reference frame, right?
Because
Right. So events which are space-like separated, they may be one of the, they are not, whether they're simultaneous or one is in the future of the other, there is no notion of time ordering between them in a strict sense. So there would be another reference frame in which, this guy would be anywhere on this, so this is a very bad hyperbola. This guy would be anywhere on this hyperbola. So you could go to a reference frame, where the relative positions of these 2 points could be like this. Okay, this is what it means in special relativity that there is no absolute notion of simultaneity. Whereas if 2 events are time-like separated, there is a definite notion of future and past. Okay, same goes from light line. But when it comes to space-like separation, there is no absolute notion of what happened before or after.
so time ordering doesn't really go away with special relativity in this sense.
No, time ordering doesn't go away. It just exists. Its absolute meaning only exists for time-like separated intervals. Okay. In Newtonian space-time, time ordering, exists for all separations, all points, between all points. But in special relativity, it's very specific to time-like separated points.
So it's kind of like they're so far away from each other that one couldn't go to the other even at the speed of light. So it seems.
Yeah, exactly. So, and there would be a different reference frame in which one would be in the past of the other and vice versa.